Thanks. Yeah. Sorry for the slight delay. I got stuck on the tube, but I'm here. It's nice to be introduced by Sebastian. Some of his audio to MIDI alignment work was a good inspiration for stuff in my PhD. So I'm going to talk about this data set of MIDI files that I'm calling the Lakh MIDI data set, and sort of describe how it was made, which is what I did during my PhD, and then I'll give a discussion of ways that you might want to use it. So just to motivate this whole idea, MIDI files are potentially very useful sources of information for music information retrieval, because they include things like key changes, obviously a transcription of the piece, meters such as beat and downbeats, as well as tempo. So potentially MIDI files have the possibility of providing us with a lot of really useful information about a given piece of music. And so sort of the goal of this project is to take MIDI files and take their information and use them to augment the Million Song data set. And for those of you not familiar, the Million Song data set is exactly what it sounds like. It's a collection of a million pieces of music and metadata about them, some acoustic features extracted by Echo-Nest, and also some 30-second preview clips from 7 Digital, so not the full audio. By the way, was anyone here at the DMRN +8 in 2013? Maybe or not? Yeah, so this slide is from that. I gave a talk that was like, this is what I planned to do, and now I'm giving a talk which is like, this is what I did. And so, yeah, coming full circle. So in order to utilize these MIDI files in that way, we sort of have to do two things. The first is we have to match them with corresponding audio recordings. So given a MIDI transcription of a certain song, we need to find the audio recording that corresponds to it and sort of match them. And the second thing we need to do is to align them in time, because the way that the MIDI file was transcribed, the timing might not match exactly the performance of the song in the audio recording. So you might think, for example, that matching is a simple matter of metadata, sort of fuzzy text matching, but MIDI files don't really have a standard or even commonly used way to store metadata. So the most common way is pretty much just in their file name, and as you can imagine, that can be extremely inconsistent. This whole project started with a public web scrape of about a web scrape of publicly available MIDI files on the internet, about 176,000 of them. And among those, maybe a few tens of thousands had what I perceive to be useful metadata in the form of their title. So a lot of the work that I'm going to talk about today is basically focusing on the problem of doing content-based MIDI to audio file matching, and also audio to MIDI alignment. And you can sort of think of the matching question as a generic subproblem of this framework of sequence matching. So you have a big database of sequences, in this case audio recordings or acoustic features of audio recordings, and you have a query, which is the score, and you want to find the entry in the database which is most similar to it. And a very effective approach for this kind of problem is dynamic time warping, which I'm guessing that many of you are familiar with. But the basic idea is that rather than computing, for example, assuming that the sequences are aligned and computing pairwise Euclidean distances, you actually do a optimization that tries to pre-align the points in time in the two sequences that you're comparing, and then you use the pairwise distances of the aligned points in time as sort of your distance measure between these two sequences. And that allows it to account for things like sequences that differ in length or have slight phase offsets or even other timing distortions, and it really can work remarkably well. And it can work remarkably well in the problem that we're talking about today, which, as I said, is comparing a audio recording and a MIDI transcription. Usually the way that people proceed to use DTW in this framework is to take the MIDI file, synthesize it using some synthesizer, computing some acoustic features, and then computing the same acoustic features for the audio recording. And then dynamic time warping, in terms of the nitty-gritty, often you start by computing a pairwise distance matrix between the two, and then using dynamic programming, you find effectively like the lowest cost path through the distance matrix. So this gray box here is the distance matrix, and the red line is the lowest cost path. And you can see that it can actually do nice things, like hopefully you can see this from back there, but the slope of this path changes here, And the reason for that is because in the audio recording, whoops, I actually need to blend this in. So this is, might not get to play the audio. I guess, let's see.
Is it coming out of your speakers?
No, it actually might be an issue with my playback. So I'll just describe to you what it sounds like. This is actually the bridge, and this is the Magical Mystery Tour. I don't know if you remember, but there's a bridge where the tempo slows down. Hopefully you all are familiar enough with the Beatles songs that maybe you can remember this. And the MIDI transcription, whoever transcribed it didn't change the tempo there. So dynamic time warping has, in this case, compensated for that, and it still managed to align the two things. But just sort of a nice example of what DTW can do. In terms of actually applying DTW, there's a couple of things that you have to consider. Like, for example, what feature representation are you going to use for comparing the two things? What distance metric are you going to use to actually compare things pairwise when you're computing this distance matrix? And what are the sort of penalties or constraints you're going to put on the path? And then when you're actually using DTW for matching, you should probably normalize the sum of pairwise distances, maybe by the number of distances that you're summing over, or the mean distance across the entire distance matrix. All of these things make it a more reliable metric, but it's not clear what the right system design choices are. So the first thing we're going to do is we're going to say, DTW works great, but there's a lot of system design that has to go into it. How can we make the best possible DTW-based audio to MIDI alignment and matching system? And the framework that we'll use to attack this problem is Bayesian optimization, which, if you're not familiar, the simplest way to think of it is that it's a framework which allows you to just take objective values, so values of some function, and it predicts where it thinks the best possible parameter settings are for that function. And in our case, parameter settings are system design choices, like the feature representation, the distance metric, the normalization scheme, and all this stuff. And we just need a way to report how good a given system is, and then Bayesian optimization will basically propose to us new systems that it thinks will work even better. And, oops. So, as I said, in order to use Bayesian optimization, you sort of need an objective value. You need a function which produces a single value which says how good something is. In the case of audio to MIDI alignment, a natural objective would basically be how accurate is the alignment system. In order to compute that, you need sort of ground truth alignments. You need for example, an audio recording and a score, and you need to know what is the correct alignment. And then you can evaluate how good is my alignment system. Unfortunately, there aren't any really large data sets of that type. So what I did here is I basically just created synthetic alignment data. I took a MIDI file, I corrupted it by removing instruments or changing notes, and crucially changing the timing in various ways. And then I synthesized that. I took the original MIDI and synthesized it, and then I tried to align these two things. And so how well the alignment system works is basically, was it able to compensate for the timing distortions that I put into the MIDI file? So here's an example of what that timing distortion looks like for the scheme that I used. You can see there's a little discontinuity around the middle. There's also just sort of this smooth warping. And if you use DTW, actually, if I use the best system that we were able to find to sort of correct for this, it comes up with a curve that looks like that, which looks effectively the same. So it's working. It's doing the right thing. It's a little easier to visualize the difference between these two curves by just taking their absolute difference, which is plotted here. So on the y-axis is the absolute error in seconds, and the x-axis is just across the time of the song. You can see there's a big spike there right at where the discontinuity was. But otherwise, it managed to do a pretty decent job. So if we take the average of this absolute difference across the course of a song, and then take the average of those across a big corpus of synthetically generated data, we have a really nice metric to report to the Bayesian optimizer. And so doing this process, we generated a handful of really nicely performing DTW systems that are highly accurate. But as I mentioned, there's one other thing we need, which is for it to be able to basically tell us when it thinks it's correct or incorrect, and also to tell us when it thinks the two things match, because we're going to be doing matching and aligning. And the matching component really depends crucially on how reliable the DTW score is, this like confidence score, this sort of normalized distances. And so there's a couple of ways to normalize those scores in order to choose which one worked best. we generated a second collection of really, really heavily corrupted MIDI files. That, many instruments were removed, the timing distortion was insane, and the hope is that for those MIDI files, it would report that the alignment failed, or that it was not a good match. And you would hope that basically the alignment score, the DTW's reported confidence score, and the alignment error were highly correlated. And so by looking at how well correlated things were for different normalization schemes, we could pick a normalization scheme that worked quite well in general. And here's an example of sort of the correlation for the best scheme that we found. So now that we've done all of this, we have hopefully a DTW system that is highly accurate and highly self-aware and able to report when it's successful and when two things match. But we've only done this on synthetic data. So the last thing we did was I literally listened to 500 audio MIDI alignments, and some of them were not matching. Some of them were matching, the transcription quality varied, and I just rated them on a scale from 1 to 5. 1 being this is not the right MIDI for this audio, and 5 being this is absolutely perfect. Perfect transcription, perfect alignment, etc. And so on this violin plot, the y-axis shows the confidence score reported by DTW, and the x-axis shows the rating. So the hope is that when we consider things to sort of be correct, which is sort of rating 3 and above, we want the confidence score to be high, and we also ideally would want these blobs to be kind of separated, because that means that the confidence score and my rating are really highly correlated and have a lot of mutual information. And you can see we get most of that here. There is some overlap, but really the system is effectively doing what we want. So at this point it might seem like we're done, because I said we needed to solve alignment and matching. And we have a DTW system that seems very reliable for doing both of those things. The problem is that DTW is just much too slow for the scale that we're doing things at. So with the system that we came up with, it takes about a quarter of a second to align a MIDI and an audio, like all of the steps in the system I just described. And we have, as I said, about 178,000 MIDI files and almost 1 million audio files. And then it'd be normalized by years, and it's going to take over a millennium. So we need to do something faster. And the rest of this talk, or for the next little bit, I'll talk about how we can make this whole pipeline faster. And by the way, feel free to stop me with any questions at any point. So the first thing that we'll do is we'll look at why DTW is slow. And the main reason is that it's quadratic in the sequence length. So if you have very long sequences, it tends to be very expensive. The other reason is that you end up computing this distance matrix, and each individual pairwise distance calculation is pretty expensive. So the first way that we're going to tackle the slowness problem is by basically making the sequences shorter and mapping them to a representation where you can compute pairwise distances much more quickly. And one very useful place to map things when you want to compute their distance quickly is into a binary space, because you can compute the distance between two binary vectors by an exclusive OR followed by a population count, which are basically two machine instructions. This is opposed to like a continuously valued feature vector, which would take, they're all floating point operations, and there may be many more of them. So we're going to use binary vectors, and we're going to also downsample the sequences. We're going to make them shorter. And when we downsample the sequences, of course, we get quadratic speed gain, so that's good. So how are we going to perform this mapping? The idea is basically just to take groups of subsequent feature vectors. In our case, these are frames from a spectrogram, and learn a mapping using two big convnets to a binary space where similarity is preserved. And what I mean by similarity being preserved is that if we have a MIDI file and an audio recording which are matched and aligned ahead of time, we want co-occurring blobs of feature vectors in the two, in the MIDI and the audio, to be mapped to similar binary vectors, with binary vectors which have a small distance. And then when we take a non-matched or non-aligned MIDI file and compare it to an audio recording, we want those binary vectors to be quite different. And that's really the crux of it. Of course, since these are convnets, we can, as long as we come up with a suitable differentiable loss function and we have the right training data, we can optimize them and hopefully they'll do the right thing. So the training data that I'll use here, as I mentioned earlier, I found roughly on the order of tens of thousands of MIDI files which had reasonable metadata, and I just pre-aligned them using the DTW system. So in that case, I didn't have to compare each MIDI to every audio recording. I just did text matching to basically filter out most of the Million Song data set, and then aligned many fewer things. I only had to do maybe like 10,000 alignments instead of 150,000 million. So that gave us the training data. For the network structure, as I said, it's just a big convnet. There's, in this particular case, 3 sets of convolution layers, each one followed by max pooling, and then at the output we have a couple of dense layers. And then in order to get to a binary space, all we do is that on the output we use a hyperbolic tangent nonlinearity and threshold around 0. So sort of the simplest possible way you could think of to get binary vectors. Last thing we need is a loss function, and conceptually think of it as I have 2 things which are similar. I want those 2 things to be far apart. I want everything else, which are shown, so the 2 things that we want to be similar are blue dots here. Everything else is green dots, and we want those to be far apart until they reach some margin, which is shown as this orange circle here. And once they get past the margin, we stop trying to push them apart. So that's all that this loss function is doing. And after we train it, it works, and here's what the output looks like. So on the top left, this is a spectrogram of one of the 7 digital preview clips, so an audio recording. And this is a spectrogram of a synthesized MIDI, and these 2 things match. So this audio recording, so this MIDI transcription is a transcription of this audio recording, or at least part of it, because again, these are short preview clips. And then after training, the output of the network looks like this, and it looks kind of like gibberish, but one thing to note is that there's these 2 things here that look kind of similar, and those are verses, or sorry, they're choruses rather. So there's some sort of obvious visual structure here. And actually, if you look at the distance matrices, which I'm showing down here, this is the distance matrix for the spectrograms, and here for the binary vectors, and actually, arguably, the distance matrix for the binary vectors has more obvious structure. So clearly it's learning something that is hopefully useful. And in particular, if you actually do DTW on the sort of spectrogram distance matrix, and if you do it on the binary vector distance matrix, you get the same alignment path. So another way to look at how well this is working is we actually can just take the groups of feature vectors that are matched and aligned in our training data and compute the distribution of distances for them, and then grab random non-matched pairs and compute that distance distribution. That's what I'm showing here. So blue, this is just for spectrograms. Blue is matching and green is non-matching. And ideally we want these to be completely separate, because it means that when things don't match, they are unrelated. So we just take the output of the network after training, you see that they get much better separated. So it's actually arguably doing something better even before we threshold it. When we actually make the binary vectors, we lose some information, but the separation between these 2 distributions is definitely a bit better. So that's all some sort of qualitative analysis. In order to figure out how well it actually works and how useful it is, what I did was take a collection, basically like a test set of known correct MIDI to MSD matches, so I know that this MIDI file is a match to this entry in the Million Song data set, of which I had about 1,000. And for each entry in this test set, I used the hash sequences and basically said, what is the rank of the correct match in the Million Song data set for this MIDI file? So ideally, you always want the rank to be 1. And this plot shows what proportion of the test set had a rank below a given threshold. So, sorry that this plot takes a little while to explain, but the point is basically you want everything to be near this top left corner, because that means that, for example, 100% of the test set had a rank near 1. And you can see we are pretty close to that. This x-axis is on a log scale, so probably the most important point in this plot is maybe somewhere around here, which basically says that with 95% confidence, we can discard all but 100 entries in the Million Song data set. So that means that we can discard 99.99% of our data set with this much cheaper representation. It's about 500 times faster to use this representation than it is to use regular dynamic time warping. So this is a very effective pruning method because it's very accurate and much faster. But it's still not fast enough, so we needed to do something even better. at least as a first step. And for that, we're actually, instead of dealing with sequences and dynamic time warping, we're just going to take sequences and map them to single vectors. So we have a sequence here, our spectrogram. We're going to pass it through another kind of neural network, and the neural network is going to output a single vector regardless of the length of the sequence. So you can think of it as just like a summary of the spectrogram. And otherwise, these systems are very similar. We just say when we have two things that are similar, in this case, that means that they are matching MIDI and audio. We want their mapped vectors to be very close together in the embedded space and very far apart for things which don't match. Otherwise, the loss function is the same and the training set is the same. We don't actually have to realign things here, but otherwise things are very similar. The crucial difference comes in the network structure. In this case, we're adding a mechanism. If any of you are familiar with the sort of attention mechanism that people have been using, especially in recurrent networks, this is very similar to that. The idea really is just to, for each entry in your sequence, so for each frame of your spectrogram, you output a scalar importance value, and then you normalize those values across your spectrogram or your sequence, and use that those normalized important values to compute a weighted average. So literally all you're doing is learning to compute a weighted average, and the importance scores are produced by a little neural network that is trained as part of the whole entire network. So in particular, as before, we're going to take our spectrogram, pass it through a few convolution and pooling layers, pass it through this feed-forward attention mechanism, which is just a fancy weighted average, and then take the weighted average, pass it through a couple of dense layers, and that will give us our embedding. And again, the loss function is the same. Overall, the training is effectively the same. So again, we can examine the output to see how well this does. So here, this is a synthesized MIDI. Here's our audio clip, synthesized MIDI audio clip. So these two match, and these two match, but that doesn't match, and that doesn't match. And you can see down here the vectors that they map to. So this is for the top two, this is for the bottom two. And you can see their vectors look quite similar, and across the non-matching pairs, they look quite different. So again, visually it's doing what we want to. Another way to sort of look at what the system is doing is to actually look at the importance value assigned by the network to each entry in our sequence, each frame in our spectrogram. And this plot shows that you can see a very faint green line, and the blue line is just the smooth version of that line. So the green line is these importance values, and the blue line is the smooth importance. And it's a little hard to reason in a justified way about what the network is doing, because you're kind of letting it decide to do what it wants to. But in particular, there's some really strong features we can see here, like when these two little sort of mid-frequency transients show up, the attention just drops. So the network doesn't like that. It does seem to like things over here, which are more steady-state things, so ports. So just to give you sort of a vague idea of what the attention is doing. As before, we can look at the distribution of distances for matching and non-matching things, except in this case, these are the embedded distances. So this is actually what's being compared. So before it was pre-DTW, and here this is like actually what is actually being compared. And you can see there's quite a bit of separation here. So as before, we can use the same test set and look at the match ranks, and you can see this curve looks much worse, especially if you use my heuristic of you should be near the top left corner. So in the same way, we can look at basically what point do we cross this sort of high confidence threshold, maybe around 95% or something. And in this case, we cross it around 10,000. So what this means is that with this approach, we can discard all but 100,000, all but 100,000 entries in the million-song data set, which means roughly 90%. The nice thing about this, though, is that it's about 500,000 times faster than dynamic time warping. Like, it's extremely fast. So this gives us something that takes almost no time and allows us to discard 90% of the million-song data set. And then we have the hash sequences, which are a little slower, but quite a bit more accurate. And then finally, with what remains after both of these pruning steps, we can do normal, expensive dynamic time warping. So if we combine all of these things, so this is the green line from the sequence embedding that I just talked about. These are the hash sequences. The blue line, you already saw that. And then if we finally use the red line here, shows if we actually do dynamic time warping at the very end, what are the ranks? And you can see we end up quite close to our preferable top right corner. So the reason that this red line doesn't ever reach 100 is because we pruned something. So this basically shows the false reject rate, which ends up being about 4% for the thresholds that I chose. Overall, this whole system allows us to, with pretty high confidence, as I said, only 4% or so false reject rate, it allows us to do this entire matching of 178,000 MIDIs to the million-song data set in about a week. So that's great. To give you an idea of the sort of confidence, actual DTW confidence scores of the things that we matched and how many good matches we had, this plot just shows the thousands of MIDI files that had a confidence score above a given threshold. So you can see there were about 50,000 MIDI files with a confidence score of 0.5 or higher. So if we take 0.5 to mean basically this is a correct match, we found about 50,000 MIDI audio pairs which were correct matches. So with that in mind, I created the Lakh MIDI dataset, which is sort of consists of 3 collections. The first is just all of the MIDI files as they were, unmodified, unmatched. The second is the matched MIDI files, so about 50,000 MIDI files which have been matched to the million-song dataset. And then finally, matched and pre-aligned MIDI files. So the final one is to take these MIDI files, pre-align them to the 7 digital preview clips, and distribute that. So all 3 of these things are available online. I'll give a link. Actually, I don't think I have a link in these slides, but I can give you a link after the talk. I have a tutorial online that I'm just going to quickly go through to show you the sort of things that I think would make sense to do with this data, and also sort of to give you an idea of how to use it. Can you read that at all? I guess that's somewhat legible. Okay, great. So first thing to mention is just how the data is laid out. Basically, there's a JSON file that associates MD5 checksums of MIDI files with entries in the million-song dataset, and also gives the confidence score of the match. So you can pretty quickly say, okay, do you have any matches of this million-song dataset entry? And if so, what are their confidence scores? And so for this particular million-song dataset entry, there were 5 matches with confidence scores ranging from 0.68 to 0.78. And yeah, that talks about the file layout a little bit. So in terms of actually utilizing the aligned MIDI files, there's potentially a lot of things we can do with this. We can maybe train transcription systems, train beat tracking systems, and I'll just show a couple of the things you can do to extract the data from the MIDI files to get some of that information. I might, let's see if we can actually play this. So, in this little example, I took the MIDI file and I synthesized it and put it in one channel, and then I took the audio file and put it in the other channel. And it's hard to hear without headphones on, but there is a MIDI file and an audio recording playing. Of course, if it was the wrong MIDI file or the alignment was wrong, then you probably would be able to hear it. So that's good. Feel free to listen to it on headphones.
Is it synthesized MIDI, or is it the actual plain sending MIDI messages?
So this is just pre-synthesized, like offline using FluidSynth, yeah. If you have a real-time MIDI thing, you could also send it real-time to a different synth. So because they're matched, you can do things like get metadata about the MIDI file from the million-song dataset. So for example, you can get things like last FM tags for a MIDI file, which is kind of interesting because it augments these MIDI files with a ton of metadata that they didn't have before. So in addition to getting the song title and artist and album, you can also get tags and danceability according to Equinest and all these other things. As I mentioned, you can get the transcription from it. So here I'm just plotting a piano roll of the MIDI the MIDI file, and here's the constant Q spectrogram of the audio recording. You can see there's some similar structure there, hopefully. You can also get like a per instrument piano roll. So MIDI files make it really easy to say, give me the notes that were played on this particular instrument. And in particular, you can also get the start and stop times of the notes. And this notebook that I'm going through gives you code to do all of this. Using mostly using Pretty MIDI, you can do any of this stuff in like 1 or 2 lines of code. So, as I mentioned, you can also get meter, so beats and downbeats from the aligned MIDI. If we play that along with the audio recording, so you can, for all of these matched and aligned MIDI files, we can extract beat locations for the audio recording that are inferred from the MIDI. So that's nice. We can also get key changes and where they occur, and then finally you can actually get time-aligned lyrics from a lot of the, just make this small. Yeah, time-aligned lyrics from many of the MIDI files. Not all MIDI files have lyrics, it's totally optional. It doesn't affect playback, so they don't have to include it. But for those MIDI files which do have lyrics, you get time-aligned lyrics, which is great. So hopefully that gives you a flavor of the kind of things you can use the Lakh MIDI dataset for. And hopefully you're all a bit excited about using it right now. But the last thing I'm going to do is talk about potential pitfalls, so things to watch out for. One of the first things that I did with this dataset after creating it was basically look for the MIDI files that had the most matches in the Million Song dataset. So what MIDI file matched the most things? And I was thinking it would be like Imagine by John Lennon, or I don't know, one of the classic like parlor piano songs. And these are the artist and song names for the most matched MIDI. And you can see they're definitely not the same song, so that's bad. But if you look closely, you might be able to start to be suspicious of what the failure mode that I'm going to talk about is. And in particular, if you look at the spectrograms, it might be even easier to visualize. And the difficulty here is basically that all electronic music with a floor-to-floor bass drum looks pretty similar in a spectrogram. And in particular, if, for example, the 7-digital clip just happened to pick up on the intro of the song, which just has the floor-to-floor bass drum, and the MIDI file was basically a floor-to-floor bass drum, then that is a very good transcription of what that audio recording is. But, of course, we can't really say, well, this MIDI file is a transcription of all 100 or all 200 of these audio recordings of all of these songs. Because it's really only a transcription of a short part of it, and beyond that, it's, as I said, the other parts of the MIDI file probably don't match, and beyond that, it's not that useful of a transcription. So that's one thing to look out for. Another sort of related, slightly higher level issue is that it's common for a cover to get matched to the original. This whole system, this whole process that I'm talking about is not terribly different from the systems that people use for cover song ID. So it's not uncommon for example, in the case of Imagine by John Lennon, there's maybe 5 or 6 covers of it in the Million Song dataset. So if you have a transcription of Imagine, it probably will get matched to the covers too, which is maybe correct, maybe incorrect. It's hard to pick a threshold around which you say, this is good and this is bad. But it's just something to be aware of. The other thing that I did to try to figure out how useful this data set will be is, something I did, I guess, earlier this year, or about a year ago, which was to basically take MIDI-derived annotations and compare them to human annotated ground truth. So to do these experiments, I took the Isophonics Beatles transcriptions, or the annotations, the key annotations and the beat annotations, and I took Beatles MIDIs, matched and aligned them to Beatles audio files, and then extracted the relevant annotations from the MIDI file and compared them to the handmade Isophonics annotations. So the hope is that the human and the MIDI file agree a lot, because you can think of the MIDI file as another source of human annotated ground truth. And in particular, you really would want the MIDI-derived annotations to work better than an audio content-based estimator. Because if the audio content-based estimator agrees with the human more, then the MIDI files are not really that useful. So the first experiment I did, as I said, was on key reliability, and I used sort of the standard Mirex score, which is just between 0 and 1. It has some heuristics to decide which keys are better to estimate wrong than others. And the mean score across all these MIDI files that I matched and aligned compared to the Isophonics was 0.4, which is quite bad. So an audio content-based key estimator, which is actually the CleanMiri VAMP plugin, got 0.687 on average. So it's worse than that on average. So the bad thing that I said could happen did happen. But interestingly, if you compare only the C major keys, so only the MIDI-derived C major keys, the score is 0.16. And if you compare all the non-C major, the key is 0.842. And 0.842 is quite close to human agreement. So I also downloaded a bunch of key annotations for Beatles songs from a website, whatkeyisitin.com. And the human-to-human agreement was 0.857. So that's a really long way of saying that for key, C major key annotations in MIDI files are very suspect. And the likely reason is that transcription software may sometimes put a C major key at the start of your MIDI file, whether you like it or not. So we're in this funny situation where we now have an insane amount of key annotations, but we can't trust C major key annotations. So it's a little funny. So as I said, the second thing I did was compute how reliable the beat annotations are. And in this case, the alignment actually also matters. So for the keys, it's on a global sort of song level. That's at least the assumption for Murex evaluation. For beats, we actually have to look at the alignment. And so for that reason, I'm also going to be looking at the confidence score. And what we would really hope is that for these beat metrics that people use in Murex, the F measure, any metric level total information gain, we would hope that when the Murex score was very low, the confidence would be very low, because that would mean that basically the alignment failed or the transcription was bad or something like that. And when the confidence was really high, the score would be really high. And you do see that trend in these plots, but they're much messier than we want them to be, right? So for example, for F measure, you see this cluster down here, which is low confidence, low F measure. So on all of these plots, the y-axis is the beat evaluation score, and the x-axis is the confidence score. And you do see some clustering up here, but there's a lot of stuff in here that, you know, it would allow us to use these annotations with much more confidence if it wasn't there. And the issue here is basically that the confidence score that I worked on at sort of the beginning of this talk is somewhat invariant to slight differences in timing. So basically if the alignment gets a little sloppy somewhere, the confidence score won't drop very much. And we kind of want that for matching, because if two things match, we don't really care if the alignment gets sloppy. So that's maybe good for the matching aspect, and not so good when you're actually using the aligned MIDI files. So I think that this mostly motivates people to either work on better confidence score reporting, or just taking the MIDI files that are not pre-aligned. So as I said, I released the pre-aligned MIDI files and the not pre-aligned MIDI files for the matches, and aligning them with a system that is better in terms of its accuracy and also in terms of its very fine time resolution confidence. And then maybe we can use these beat annotations with more reliability. So just in summary, I hopefully motivated to you why MIDI files can be extremely useful for music information retrieval. I talked about creating a DTW-based system that was both accurate and gave us a useful confidence score for matching. I talked about a way to make the dynamic time warping much faster by using shorter sequences of binary vectors. And then another way to make the whole system even faster by collapsing entire sequences to a single vector that encoded sequence similarity. And then I talked about the actual matching process, and finally gave some qualifications as to actually the usefulness of this data. So yeah, that's all I had to talk about. I should mention that I usually put a slide at the end of my talks with a bunch of links, but I like these pictures more. But all of the code for my thesis is available online. My thesis is now online, which is great, and the Lakh MIDI dataset is online and freely downloadable. So I hope some of this ends up being useful to all of you. So thanks. Yeah, happy to take questions, of course. Yeah.
I have a very pragmatic question. How, because you said that for the million song dataset you only had the preview clips.
Mm-hmm.
So how long are these clips, and how much music do you have on total aligned between MIDI and audio?
Okay, yeah. So the preview clips. There's a good paper that's not mine that talks about the preview clips called. I'm not going to remember what it's called, but they have a nice plot that shows the distribution of preview clip lengths, and they're almost all, like most of them are 30 seconds. Many of them are a minute, and then there's a couple, outliers. In terms of the actual number of MIDI to audio transcriptions, given that heuristic, and given that I have roughly 50,000 matches, there's somewhere in the order of tens of thousands of minutes of MIDI aligned to audio recording. Of course, if you somehow have access to the full songs from the Song Dataset, you could rerun the alignment and get more audio. And also I should mention that because the code is available, if you have like a private collection of MIDI files or a private collection of audio recordings, and you don't want to use the dataset that I released, you can still rerun the matching process. It'll take some time,